All right, so let's go over these problems. Ooh. Okay. Let's go over these problems. I'm going to try to draw on the board here so we can get good at identifying electron density. So in this problem, CH3, CH2, CH2, CH2. This is an 11 carbon chain. I think we counted it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, it's 11 carbon chains. Decade. All right, so do carbon and hydrogen have differences in electronegativity? Is a carbon-hydrogen bond polar? It's the same, right? This is a non-polar bond. So you can actually imagine this as, if you visualize what it looks like. CH3 looks like this, right? And then CH2, right? And then CH2. Okay, so this is just a condensed version of the Lewis structure. So all these bonds are nonpolar, nonpolar, nonpolar. A carbon-carbon bond is obviously nonpolar, 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 nonpolar. Right? If everything is the same in electronegativity, then they can't be polar. So what color will we color this entire thing? Green, right? We color it green. So we color the entire thing green. I don't know how well this is showing up on the camera. I try not to pick super, super dark green because I've got one dark green that's bigger but make it really hard to see. You color the whole thing green, right? Because there is no difference in electronegativity here. So this whole thing looks green. My marker's about to be dead too. See if I've got another one. That looks better. Okay, whole thing's green, right? There's no portion of this molecule that is polar in any way. You also remember back to what we talked about on Monday, right? If a molecule is a hydrocarbon straight up, no modifications to it, by definition, it's going to be nonpolar because it's a nonpolar bond between carbon and hydrogen. Are we good on this one? All right, let's look at the next one. Oh, we forgot to list the intermolecular forces. What intermolecular forces are in this? London, anything beyond that? Nope, London forces only. Good. All right, now let's look at the next one. Oop, that's too high. There we go. Okay, so the CH3 portion, what color is that going to be? The CH3 part right here? Carbon and hydrogen, is that a polar bond? No. So again, if you want to expand this out, right, CH3 looks like this. Right? That's what that looks like. So is that part polar at all? Nope, that's nonpolar. So what color would nonpolar be? Green. That's our green. Oh boy, that looks blue. That's not a good pick. That's definitely not blue. I have to keep that in mind if I want a blue. There we go. Okay, now we talked about this on Monday. What is a C double bonded to O called? It's got a special name. Well, it's capable of dipole-dipole. Yes? Carbonyl, right, that's a carbonyl. So this portion right here is capable of dipole-dipole. And so that means that there's a positive and a negative part, right? This part here is partial positive. This part here is partial negative. Can't really see that. So that means that this is like a light red, right? And then this is like a, where's that green that looks actually blue? This is like a light blue. Now it looks green. Can't win with colors on a screen here. Let's try that color. Okay, light and light, okay? Now I make the point of pointing that out because in the OH, there's a big disparity. Where's the partial positive? Where's the partial negative in the OH? Backwards. Oxygen's going to be the positive, the negative, and then it's going to be dark. Okay? And then this one is going to be dark. Okay, so you have a big disparity there. This is like, I'm trying to make it darker than this one. Okay. So when we're listing the intermolecular forces, we'll have London, right? We'll also have dipole-dipole. And that comes from this part right here. And we'll have hydrogen bonding. We'll have all three. Make sense? Okay, let's do this one. We've got an OH, right? So we already know that's going to be the same, right? Because we're going to have dark red and dark blue. And dark blue. Is the rest green? And then the rest is green. That's right. Now we could compare these two molecules in terms of their boiling points because they are similar in size. Right? These molecules are similar in size. One of them's got London and H bonding, right? Whereas this one's got London, dipole-dipole, and hydrogen bonding. So who's going to have the higher boiling point of these two? Right, this one boils at a higher boiling point. And it's going to be a pretty significant difference, right? Because having that carbonyl makes a big difference in the boiling point. It makes a big difference in the intermolecular forces. Do we understand this one? Okay, we'll go ahead and do argon. Argon's a monatomic element. So can you share something unevenly with yourself? No, so the entire thing's green. And that little line is just because it's a word, and it's mad at me because that's not a correct word, I guess. London forces only, right? Nothing else. Any questions on those? All right. Oh, goodness. Yeah. Some color behind. All right, let's see what we have next. Oh, still have one more color. Okay, so what's this one going to look like? Someone talk me through it. Green. Green, good job. Good job. Good. And then green. And then in terms of intermolecular forces, very good. And it's not, the dipole-dipole is only focused on which part? Yes, carbonyl. Right. Good job. So the dipole-dipole specifically is that part right there. No, I just want you to know where it is. Okay. It's not because of this, it's because of this. Good job. All right. Let's go over the last few before we run out of time here. Okay, oops, too high. CH4 versus CH3CL. So here are the Lewis structures. Versus CH3CL. Okay, what IMFs do we have? Is this one polar or non-polar? Non-polar, so it's just London, right? This one obviously has London because everything is London. Is this a polar molecule? No. Yes, yes, it is. Right? So because it's polar, that means it's a dipole, right? Polar molecule and dipole are synonyms. So what other intermolecular force does this have? Dipole-dipole. So who's going to have the higher boiling point? This one's got the highest boiling point. Again, it's a significant difference. All right, and the next one, xenon versus argon. They're both monatomic, right? So we're not looking at a molecule, we're looking at single atoms, but there is going to be one with a higher boiling point. How do you decide? Molar mass. Specifically, we're looking at number of electrons, right? Polarizability. So how many electrons does xenon have? Xenon? Oh, I'm sorry. 54, right? And how many does argon have? 18. So this one's going to be the higher boiling point, right? And the explanation would be more electrons equals higher polarizability. And what is polarizability? It's the probability of having that instantaneous dipole, right? Because it is probable to have electrons be on one side of the atom at a higher proportion than on the other, right? Because they're random motion. So polarizability is the probability that you'll have those instantaneous dipoles. Because both of these have London forces only. So now what we're doing is looking at polarizability, which is the deciding factor. Does this make sense? Makes sense. All right. Let's go over the last three. We've got time, we're good. Okay. CH4 versus CCl4 versus CBr4. So, Lewis structures, CH4, CCl4, versus CBr4. Okay, so are any of these polar molecules? No. No, they're all nonpolar. So now all we have to do is, what's going to be the deciding factor? Okay, polarizability is going to come back into the picture here, right? Because these are all tetrahedral, they're all carbon in the central atom, right? And so they're all nonpolar though because they're all symmetric. Even though a carbon-bromine bond or a carbon-chlorine bond is polar, this is symmetric, this is symmetric. So now we look at the periodic table. Bromine has 35 electrons versus chlorine, 17. So who's going to have the highest boiling point? So this one's got the highest. Who's got the lowest? Methane, right. And then this one's the middle. Questions on this one? All right. So they were already ranked for us. The next one we're looking at ethanol versus propanol. So I've given you, oh, versus butanol. Oh, I can't fit that on there. Okay. Ethanol versus propanol versus butanol. So ethanol is, that's a 2-carbon chain. Propanol, 1, 2, 3. One propanol. 1, 2, 3, 4. OH. So ethanol versus 1 propanol versus 1 butanol. Okay, so this is shorthand notation, so I don't have to draw out all those carbons and hydrogens. So all of these have, what are the IMFs in all three of them? London and what else?
Hydrogen.
Hydrogen what? Bonding, right? Okay, so they all have the same IMFs. So what are we looking at as the deciding factor? Chain length, right. Longest chain, shortest chain. So who's going to have the highest boiling point? The longest one, right. So this one's the highest boiling point. This one is second highest. And then this one is lowest. Getting them right? All right. Very exciting news. Okay, last one. H2S versus H2O. So, H2S has a Lewis structure. S, H, H. Right, that's tetrahedral molecular geometry. Water is the same way. There's the Lewis structure, but when you do the molecular geometry, it's tetrahedral. Okay, let's do the IMFs. Let's do this one. London. London as well. Okay, is this a polar molecule?
Yes.
Yes, it is a polar molecule. So it's a dipole, so that means it has dipole-dipole. What about this one?
Yes.
Would it have dipole-dipole?
Yes.
Are you sure? It has an OH bond. So what does that mean? It has hydrogen bonding. So who's going to have the higher boiling point? This molecule with hydrogen bonding, right? So water has a higher boiling point because it's capable of hydrogen bonding, whereas H2S only has dipole-dipole. Good job, guys. Any questions on these? All right, that's where we'll stop. So I'll see you tomorrow.